Okay, we're talking about the technical bases of gas centrifuges and how they operate. In this lecture, we're going to talk about some of the materials of construction and what the parts of the centrifuges are. So here's an example. On the left-hand side, here's the schematic of a centrifuge. And probably you may have seen this before, but in case you haven't, we'll talk about this for a minute. A centrifuge is a thin-walled, hollow cylinder, and gas is put inside that thin-walled cylinder, which is going to be rotating at a very high rotational speed. And the centrifuge rotor is in a casing, and the casing is maintaining a vacuum, very low pressure area, and it's also providing protection in case the centrifuge crashes or breaks. And in this picture, we have the molecular pump at the top, which works to keep the vacuum. Picture here at the bottom, we see that there's a needle bearing on the bottom of the centrifuge. On the top of the centrifuge there's a suspension there with magnets to lift some of the weight off of the rotor and also to hold it in place. And there's a bottom scoop that is removing gas, that in this picture here, that would be removing depleted uranium. And at the top, there's a baffle that's rotating with the rotor, and there's a scoop behind that in the baffle chamber that's removing the product gas. That is the gas enriched in uranium-235. So the feed material comes in, there's a post, a feed post, and the material comes in a pipe in that post, and then there's two more pipes bringing out the product material and the tails or waste material. We see that the arrows there are showing the direction of the countercurrent flow. So there's flow coming down the wall on the right-hand side, and there's going up near the axis. It's actually going down the wall on both sides in the picture. Okay, and then so this is showing a bellows. So a bellows can be used to put two rotor pieces together so that you can operate at higher speeds. And the bellows shown there in this picture. Now here's a picture of in the middle, that's a picture that was shown, picture of a centrifuge that Iran brought to a meeting. And so this is a P1 centrifuge. The scale is not the same as the ones on the right, which are American centrifuges in Piketon, Ohio. The centrifuge in the middle is about 2 meters. The ones on the right are on the order of 40 feet. So if you're going to build a centrifuge, what is it that you want to have? Well, some components that are going to be rotating, and the rotating components are rotating at very high speed. And so the rotor tube itself is first thing that you need. And then you need bellows or rings to connect rotor tube sections together. You need baffles, and you need the top end cap and the bottom end cap. The end caps are what close the hollow rotor at the top and the bottom. All those things are rotating. Now, centrifuges they rotate at hundreds of meters per second. And so when we talk about meters per second, that means it's like when you're driving your car on the highway and you're driving 60 miles an hour, then your tires are rotating at 60 miles per hour. So that's the linear speed of the rotor on the wall. So these things, these rotating components are going to be subjected to very high stresses. And so you have to have the right kind of materials that will withstand those stresses. So some of the simplest material, the ones that everyone started with, is aluminum. So there's a high strength aluminum, and this is a tensile strength, 67,000 PSI, pounds per square inch. Barraging steel, the minimum ultimate tensile strength is 300,000 PSI. And then there are composite materials. So that's the progression in which most development programs in the world pursued. Aluminum is easy to get, and you can make a centrifuge from aluminum that works. You want to make it separate more, then you want a higher speed, and you go to miraging steel. It's a little bit less available, a little bit harder to get. Then high strength composite materials, and so there are different fibers that you can use to make a composite material. But those rotating parts require these kinds of materials. Other components that you have in your centrifuge include magnetic suspension bearings that are used at the top of the centrifuge. There are bottom bearings and dampers to affect the rotor dynamics. The molecular pump, as you saw in the picture, and the scoops that are withdrawing the gas at the top and bottom, and then high-speed motors that drive the centrifuge at the required speed. So these are some of the things that you need in your shop before you start putting a centrifuge together. Now, the centrifuge performance or capacity is related to, it's called separative power of the centrifuge, and that's written there as delta U. And the separative power of a centrifuge is directly proportional to the length of the centrifuge. And it's proportional approximately to the square of the peripheral speed. So that means that if you make your centrifuge twice as long, you would get twice as much separative power. It means if you increase the, if you double the rotational speed, you'll get 4 times as much separative power. So there's a big emphasis on spinning your rotor faster, but also in making it longer. So those two things go together to get more separative power from your gas centrifuge. So if you have a small one, you want to make it bigger, then you work on the length. And if it's spinning at one speed, you want to spin it faster, you might need to go to a different material to get more strength. Now, the length of the centrifuge is a very important consideration. It's got to fit in your cascade area, and it's going to be related to how much separative power you get. The more power your centrifuge has, the more separation capacity it has, then the fewer centrifuges are required in the cascade. But when you spin a rotor, a hollow, thin-shelled rotor in particular, then as it's spinning, it goes through modes of vibration. It's very analogous to a string. And if you have a guitar string, for example, and you tie the guitar string is tied down at both ends, and you can control that. But when you pluck the guitar, then it vibrates at different modes. It has different mode shapes. If you take a string, you can make a string go through different mode shapes. So the rotor actually bends when it's rotating, and that bending it has modes, and there's a node. There are nodes for the modes. Each mode, how fast you're spinning it determines what frequency these modes are operating at. And so you can calculate the critical speed, or the natural frequency, and the natural frequency of vibration on the left formula there is A sub n times the square root of E times I divided by mu times L to the 4th. Well, L is the rotor length, mu is the mass per unit length, I is the moment of area, E is the longitudinal modulus, so that's a material property. A sub n is determined by how you're mounting your rotor, or how you're holding your rotor. So it depends on the bearings and the structure. But you see, if you make a really long rotor, then the natural frequencies go down, because L to the 4th gets larger, it's in the denominator, so the natural frequencies get smaller. So if you have but you can control things through your material. E is very important there. The Zippa, who pioneered a lot of the centrifuge work in the world, Gurno Zippa, his first centrifuge was subcritical. That means that it was spinning at a frequency that is lower than the natural frequency of the rotor. And then, so it was subcritical. To go supercritical, to spin your rotor at speeds that are higher than the natural frequency. If you go above the first natural frequency, then it's supercritical. You can go above as many frequencies as you can achieve. But a homogeneous rotor is one that is all the same material from the rotor, just one homogeneous material. And it can traverse several of its flexural modes. Then you can have a non-homogeneous rotor, and that non-homogeneous rotor has sections of rotors that are connected together by a bellows. So you need to think about the material, the rotor length, when you're building your rotor. Here's some examples for a thin-walled rotating cylinder. The maximum speed is determined by the rotor material. And on the right-hand side, the maximum speed squared is equal to sigma sub m divided by rho sub m. Sigma sub m is the tensile strength of the material. Rho sub m is the density of the material. So what you really want to make your rotor out of is something that's very lightweight but very strong. And if you look at the table on the left, if you look at an aluminum alloy, the tensile strength is given there in megapascals, and the density in kilograms per cubic meter. The maximum velocity that you can achieve without the material breaking is given in the column maximal peripheral velocity, and then the last column shows the rotor operating velocity. You're not going to operate your centrifuge at the maximum velocity. You're going to be somewhere below that to be conservative and hope that it doesn't break. So you can see with aluminum, you can go to approximately 350 meters per second. For a titanium, approximately 400. Miraging steel, 480. Glass composite, 550. Kevlar composite, 600 meters per second. And carbon, there are no data published on what can be achieved there. But the maximum, a reasonable maximum, and when you make the material, it all depends on how you wind it and the angles of the fibers and the epoxy, and there's lots of different things. But a reasonable estimate is 1,000 meters per second, and could be a little more than that. That's not an absolute number. So why do you want different size centrifuges, different speed centrifuges, and so forth? Well, there are meetings that occur every few years, international meetings. It started off being called Workshop on Gases in Strong Rotation. They changed the name in 1987 to Workshop on Separation Phenomena in Liquids and Gases. Well, one of those workshops in 1979 was held in Rome. And at that time, people were wanting to compare their computational methods, see if they got the same answers from their different methods of approach to solving the problems. And so they defined a hypothetical centrifuge. It was called the Rome centrifuge. So that this centrifuge doesn't exist, but there's a number of parameters that go with it. There are different length and diameter and operating speeds. And it was the parameters defined a large centrifuge that would be somewhat like the American centrifuge. But at the meeting, the separation phenomena in liquids and gases in Brazil in 1996, it was held at Iguacu Falls. And a second centrifuge a hypothetical centrifuge was described, and it's more like the Russian centrifuge. So the parameters that went into that, it's a shorter rotor and different speeds and so forth. So that gave two sets of parameters for scientists and engineers to use in comparing their codes. It's all hypothetical, so this information was unclassified. So the Rome centrifuge there on the right-hand side, you see it's big, it's in blue. Iguacu is a little guy, and an average strange-looking person shows sort of the height there to make things relative. So the units are shown there, the radius, height, wall pressure, wall speed, temperature, feed rate, separative power, separation factor. So the feed rate is given in both milligrams of uranium hexafluoride per second and in kilograms of uranium per year. So the Iguacu centrifuge, see, has a radius of 6 centimeters, the Rome centrifuge 25. The Iguacu centrifuge has a height of 48 centimeters and Rome 500 centimeters and so forth. So the optimal separative power of the Iguacu centrifuge is 4.41 kilograms uranium per year, or SWU per year, and the Rome centrifuge is 53.5. Optimal separation factor is 1.24 for Iguacu and 1.306 for Rome. And so when you talk about the optimal conditions, you vary the operating conditions, you vary the temperature gradient, you vary the scoop power, you vary the feed rate, and all these things are varied as parameters in order to determine the optimal operating conditions for each centrifuge. And then those centrifuges will be put into a cascade. So if you have these two centrifuges as your models and you want to design a cascade, how different are the cascades going to look? So you can calculate an ideal cascade, which are based on these optimal parameters of separation factor and feed rate, and the target parameters of product, tails assay, and product rate. An ideal cascade, by its mere name, is something that you cannot achieve exactly, but it's the ideal that you work towards. And the ideal cascade has 54 enriching stages, 5 stripping stages. And the Iguacu cascade has 59 enriching stages, 5 stripping stages. Total stages, Iguacu is 64, and for Rome, 59. The number of centrifuges, Iguacu centrifuges required is 1,031, and with the difference in the Iguacu and the Rome in doing this calculation is the separation factor. So in the ideal cascade, we're comparing an ideal cascade with the parameters, the optimal parameters of the Iguacu centrifuge with that of the Rome centrifuge. But if you look at what's called a squared off cascade, that's when you actually start hooking these things together. The ideal cascade, as you see, has fractional numbers of stages, and it's really hard to make a fractional centrifuge. Iguacu has 1,031.44, Rome 88.40, so you cannot have a fractional centrifuge, but that's an ideal number. So you have to square it off, and when you square it off, you still have the same number of stages for the Iguacu and for the Rome centrifuges, but squaring it off, you have 1,039 Iguacu and 117 Rome. We see that this calculation that the Rome centrifuge cascade makes almost 93% U-235. Iguacu gets to just over 90%. See, the tails concentrations are both approximately 0.3, and we have feed rates vary a little bit for the cascades, and we have that the efficiency of the Iguacu centrifuge is 99.4%, so it's almost an ideal cascade. The efficiency with the big centrifuges is 78.3%, so there's over 20% of the efficiency that's lost with the big centrifuges. So in this picture, the stage number is on the vertical axis, and the number of centrifuges is on the horizontal axis. So the feed point is, this is the feed point here, and we go up the cascade, stage number. This is where the tails come out, this is where the product comes out. So this is where the feed stage has the most number of centrifuges, and then they have fewer centrifuges as you go up. And this is a plot with the ideal and the squared off. The squared off is almost exactly the same as the ideal. You can't see any difference in those lines, in the colors there. On the right-hand side, you have the Rome centrifuge, and you try to square that off. So the number of centrifuges, we don't have to have as many centrifuges. This is the feed stage here, and as you go up the centrifuge, when we get to this top part, when we get up here, we have the squaring off is approximating the area under the ideal curve. And how do you approximate that? Well, you can't approximate it with the big centrifuges, and so the ideal is the red line here, the squared off is the blue line, so it doesn't do a good job of squaring off. So that's a handicap if you're trying to use the big centrifuge to make enriched uranium as high as 90%.